Okay, and Nick, what do we get out of our omnibus test or our omnibus ANOVA test? What is a, say we find a significant, our ANOVA model is significant, we have a significant F test, what does that tell us?
That means that there's a difference somewhere between your samples.
Exactly, there's a difference in there, I guess, again, to just be precise, technically we're talking about, we're claiming evidence that we have evidence that there are differences in the respective populations from which our samples were drawn, right? Because again, our tests are always talking about differences in populations as opposed to our samples. But our test says that, yeah, there's a difference in there. At least one group is different than the other group based on the data that we've collected, right? So we went through, talked about formal assumptions, homogeneity of variance, normality, independence. These are just an extension of the assumptions that we talked about for our independent sample t-test. Went through screening in SPSS and Stata. Did anybody take a look at that yet? All right, you did, okay. Pretty straightforward, okay. It's not that much different. You just have more groups to deal with than before. So with when you're going through screening for your ANOVA, you just have to make sure that you're splitting your file, looking at distributions and outliers and things like that individually within groups, and everything else is pretty much the same there. We talked about violation of assumptions last time. Just like with our t-tests, our means-based tests are fairly robust to a lot of different types of violations. Where we start to get into trouble is we start doubling down on violations, right? So if this is a methods thing. If people are looking on other people's papers, then that's a problem. But if we have our data, our groups are have distribution across our groups have wildly different shapes, right? One has a massive positive skew, the other has a massive negative skew, combined with unequal variance, that's problematic. Unequal variance and unequal sample size, violations of normality and small sample sizes. As we start to double down on things, that's when stuff starts to get problematic and we start to have less confidence in our tests. I have come up with what I believe to be a fantastic metaphor. I'll put that together and shoot that out for you just to really lock that in. I'm excited about this. I've been thinking about this a long time. But if we do have cases where we have unequal variances, unequal samples, what we're going to do is we're going to request a Welch test, right? Welch test is going to give us a correction to our F and our degrees of freedom, and that's what we're going to look at in terms of determining our overall omnibus tests here, okay? Talk about reporting, how we go through reporter F statistics. So here, again, we go through in those screencast videos, walking through the screening and the execution of a one-way ANOVA in SPSS and in Stata. This is just what it looks like. We go down through the same place where we got our independent sample t-test. We go to analyze, compare means, but now we're going to go down to one-way ANOVA. Everything ends up being pretty straightforward with that. You've got your handout and a video demonstration. You shouldn't have a problem walking through there. This is our ANOVA output in SPSS. Descriptive statistics in this case, we're looking at two different outcomes. We're looking at differences across our racial ethnic groups in terms of emotional valence in response to this amusing film that we showed them, and then emotional arousal. So we've got our ends, our means, our standard deviations, confidence intervals for our mean stuff, min, max, all good stuff there, right? And here we have our test of our homogeneity of variance, okay? And Kate, if we're looking at our homogeneity of variance test, what are we seeing going on right here?
Well, it looks like the valence one.
Mm-hmm.
That one looks fine, but then the arousal one looks like it might be some.
Perfect, right? So valence looks like it's fine. We don't have much evidence that we violated homogeneity of variance assumptions, which is good, right? Because we have not wildly, well, I mean, we have different, it's not a balanced design, right? It's not as bad as it could be in some situations, but it's not perfect. And so we notice that we have an unbalanced design, so we start to know that our tests start to become more sensitive to violations. But then if we look at our emotional arousal, right, we do see that we do have violation, right? We do have evidence. Now, Levine's test, like anything else, if I have cell sizes of 500 apiece, and I find Levine's test, Haley, am I going to be super worried about that? I don't know, maybe not, right? What I want to do is actually look at the magnitude and the difference in variances. We have an F max statistic we can talk about in terms of sort of seeing, this is a statistical test like any other statistical test. If I have a ton of people in there, it's going to be super sensitive to trivial differences, right? But in this case, I mean, we've got nice cell sizes for some of these, but it's not something where we'd be too worried that our Levine's test is hugely overpowered, and so it looks like we do have violation of homogeneity variance assumption here. And combined with our unbalanced design, that's something we should probably take serious, okay? So if we go down through, we take a look at our ANOVA table here. This is our between groups sum of squares, right? But remember that this is just variability. We call this our sum of squares treatment for sum of squares effect. This is just going to be variability that's measuring differences across groups. Remember that in ANOVA, when we say variability, we're talking about differences, right? So this is measuring, this is giving us a sum of squares being a metric of variability across our treatment groups or across our levels of our IV. Here's our within groups. What's our within group sum of squares correspond to, Laura?
It's like the variance within factors.
Yeah, variance within factor, right? Because if this was a perfect model, if the only thing that determined ratings of valence was racial ethnic group, what should everybody's score within that each group be? Should be identical, right? But it's not. There's other stuff going on. There's going to be random error, there's going to be individual difference stuff, there's going to be systematic error stuff that we could potentially predict, but we don't, right? So for the purposes of this model, it's error. That's what's going on here. And then here's our sum of squares total. This is all the variability and all the scores that we've got. Our degrees of freedom, and then our mean square. What is mean square code for? Variance. This is just a variance estimate. Just like the variance estimate, like if I asked for the variance of valence for this group, okay? This is your variance between groups, between your group means. This is your variance within groups. This is just a pooled variance estimate. That's all this is, okay? So this is a pooled variance estimate, but this is our mean squared error. This is going to be a crucial statistic. You want to know where this is, find it. Take our mean squared effect divided by our mean squared error, gives us our F test, and then our significance value. Amanda, what is our omnibus test for emotional valence telling us? It's right here.
I don't remember where the cutoffs for significance are.
Yeah. So this is just a p-value.
Okay.
Right? So what is this telling?
Then it's not very significant.
Right. So we would say, given the data that we've been presented, we don't have sufficient evidence to conclude. We don't have evidence for reliable differences in emotional valence across population of these individuals, right? So we would fail to reject, right? So we don't sort of have much going on here. Now we can go through, these are decent sized samples, but they're not huge samples. In the video we go through, calculate eta squared, omega squared for both of these, and it looks like there's reasonable effect sizes here, right? If we take our sum of squares between divided by our sum of squares total, that gives us our eta squared. Work through that in the video, and so I wanted to go through and take a look, we can go through and do that here. So doesn't look like we have strong evidence for differences in ratings of pleasantness, unpleasantness in response to this video across our groups, right? But what about emotional arousal? I mean, where would we go to make an interpretation of our omnibus effect here?
Let me go to the bottom
Yeah.
column, so the 0.05.
Oh, sorry, you got ahead of yourself. So do I go to this one?
No.
That's right. Why? Anybody have
Oh,
one?
because you had a violation of your homogeneity.
I have a violation of homogeneity of variance, right? That says that we're not super confident that this is a spot-on test, right? We've lost confidence in our omnibus F test, the one that we would usually do. But what we've done is we've created or requested this Welch test. And if we go down here, hey, what are we saying in terms of whether we reject or fail to reject sort of our omnibus test of equal variance or equal means across populations?
We can reject the null.
We reject the null, right? We're saying based on our Welch test, right? And this is important because here we've got something marginal, right? And we're not going to put, if there's no bright line, right? Like, well, we're just looking like, it's kind of it. But here we're saying, okay, well, it's 0.037, right? We can have a debate on whether or not that's super compelling evidence or not. Greenwald would say, nah, maybe, right? But what we would do is, because we've had a violation there, we would go down to our Welches and say, yep, it looks based on our corrected test that in terms of emotional arousal, we do have some evidence to suggest that there may be differences in how emotionally activating different racial ethnic groups are reporting this amusement film to be. Okay. People kind of seeing where we're at with our output here in SPSS. Any questions about this? Okay, cool. And I'll walk you through this in the screencast video too, so that'll be a reminder. If we're working with SATA, a little bit different. So we'll go through and just request our homogeneity or variance test here. ROVAR is our command. ROVAR for valence by ethnicity. Arousal, this gives us, so we've done 2 of these. Here's our Levine's test for valence. Here's our Levine's test for arousal. It's going to be the same values you get out of SPSS. Here's our ANOVA model in STATA. Again, same table. The only thing you'll see here is a model, a row of model-based statistics. You'll see that this is the same as the effect. This will be different. So this is just testing whether or not the overall model is statistically significant. Here in one-way ANOVA, you only have one predictor, so these 2 things are the same. But here we would typically be looking at sum of squares effect, sum of squares error, total, degrees of freedom, mean squared, effect, mean squared error, our F-tests and things along those lines. Okay. Other thing we can do, so here we found that we have evidence for a violation of homogeneity variance. What we can do in STATA is then ask for a W test for arousal, and now this just gives us our Welch test here. So you're just requesting that separately. Nice thing about STATA too is it'll give you a nice means plot of your marginal means with confidence intervals, right? So we can go through and take a look at that. And then the other nice thing too with this program is we can just request our effect sizes. So once we've gone through and ran our ANOVA model, STATA has what's called post-estimation commands, and so you just estat esize is just going to create, calculate effect sizes based on the last model you ran. In this case, it's our going to be our arousal model, and so we get eta squared here, omega squared here, and then confidence intervals around eta squared. This point just means 0, right? Because you can't have a negative eta squared, right? You can't predict negative variance in something. So it would be 0 and then upper and lower confidence bounds. So some nice things that this program does that SPSS doesn't do readily for you in terms of just calculating these. Okay. So we've got our omnibus test. Now the question is, what do we do with this, right? We've got for our emotional valence, or excuse me, emotional arousal, we say it looks like, yeah, there is a difference in there somewhere, but where is that difference? How do we go about probing this omnibus effect, right? So again, our test tells us that at least one population differs from the rest, but in order to see where these differences are occurring, we have to perform some follow-up tests. Now, classic approach to ANOVA requires that you have a significant overall F before moving on to your follow-up tests, right? I run my omnibus ANOVA, and if I have an omnibus effect, then I can proceed with my follow-up tests, okay? The assumption is that if you don't have evidence on the front end of a significant omnibus test, if you don't have evidence of significant differences across the whole set of groups, it doesn't make sense to go in and start digging around for stuff that might actually be teased apart, okay? But if you read your Howell text, and other people in certain areas really question the utility of your omnibus F, right? The argument is your omnibus test is going to be, if I have, say, 4 or 5 different means, 4 or 5 different groups that I'm looking at, and one group is sort of different than the others, but it's just one of 5, that difference can start to get lost in that overall omnibus test, right? So you might not detect that one group, and particularly if it's a group that you're really invested in, that can sometimes get lost in your omnibus test. If we're thinking about trying to manage our family-wise error rates, if we include our omnibus test and correct for the omnibus test and then correct for all the follow-up tests, what we can do is start to have too much correction, right? We're always concerned about, convention tells us to be worried about type 1 error, but really our bigger problem is type 2 error, right? It's, not failing to reject the null hypotheses when there's an effect to be had. And if we start to go through and correct for our omnibus test in addition to follow-up tests, what ends up happening is we've corrected for a test that now adding to the burden, threshold of burden for claiming statistical significance. We'll get to some more of this in a moment. And this is probably the most compelling argument here, that your omnibus test, this is just something traditionally that we've done. Like historically, this is how we put things together. But the omnibus test is rarely of interest, right? You're never going to hit a study where we just run an omnibus test back. Yep, there's differences in there somewhere. On to the next thing, right? We're not running our analyses to see if there's an omnibus test in general, right? We generally want to say, oh, is this group different than that group? Or are these 2 groups similar, comparable to these other 2 groups, right? And so the whole idea of running an omnibus test to gain entry to looking at other the tests that we're really interested in, people will say is not terribly defensible, right? And so from a methodological standpoint, from a strong experimental standpoint, physiologists do this a lot, right? We'll just skip the omnibus test. I'll run an ANOVA design, not even run the omnibus test because who the hell cares? What I've got is I've got very specific hypotheses on whether or not this group is different than that group. And so I'm just going to jump straight to the comparisons that I have. I don't care about the omnibus test because it's a waste of my time and just an extra step that is sort of not necessary for anything, right? So very different conventions, right? I think traditionally running the omnibus test and then running the follow-up test is probably an easier thing to get by because that's what everybody does. But I think a very, very strong argument to be made is saying, if I put together a design and I say, the whole reason I'm doing this is to see if this group, this experimental group, is different from these other 2 conditions, I don't care about the omnibus test to give me entry to go through and do that. I'm going to test the thing I put the whole design together to test in the first place. Okay? And Hal does a nice job of sort of walking through the logic behind this. Questions on this?
What's the flip side of that? Why isn't everything just converting to Howell's argument?
Well, I mean, I think sort of
What's the
conventionally,
benefit of?
conventionally the concern is that I don't actually have very specific ideas about what's going on. I'm just running some stuff to run some stuff, right? I got access to a data set that has 7 different groups, like sort of 7, and sort of racial ethnic stuff is this is a huge problem with this back. Oh, I'm just going to see if people differ based on racial ethnic background. Like, why? Because I can, I guess, right? And not have a good, strong theoretical reason to go through and do that, right? So now, if that's the case, if this is just an exploratory venture, then this omnibus test helps us from sort of digging through and then finding the two most extreme groups that do reach criteria for statistical significance, and then making a big deal about that because we found something when it's maybe not.
Okay.
Questions about this approach? Okay, so if we're thinking about the benefits of our ANOVA model, one, we say it's more efficient because we can just run one ANOVA instead of running a bunch of pairwise tests. Once we get our omnibus tests, then we got to do something with that. We got to run those tests anyway, so and that's not super helpful. Avoids complication with type 1 error, right? Instead of running a whole bunch of tests, I can just run one test and then avoid sort of compounding error with multiple tests. But if I do find an effect, then I have to jump in there and run more stuff anyway. Then I actually made this worse because now I've just added another test that then I have to follow up tests with anyway, right? And so really, from a methodological standpoint, the only thing that probably the biggest benefit of ANOVA models is that it sort of gives you flexibility in designing the experiment and saying, hey, do we have evidence that on average, so do we have some signal that the means of these populations are different across these different groups? And if the answer is clearly no, cool. That saves us from having to go in and do a bunch of stuff that's just going to turn up null anyway, right? When we do this, right, it's going to involve multiple tests, and we have to start thinking about managing our type 1 error. Just some terminology. If we're talking about per comparison error rates, this is our probability of committing a type 1 error for any given test. We set this as our alpha level, right? That's saying for any individual test, we're willing to, and generally alpha is 0.05, we're saying 5% of the time we're willing to make an error where we're saying that there's a significant effect when there actually is none, right? And we do this in our statistical tests, just again as our alpha, we just set that per comparison. But we can also start to have concerns about something we call error rate per experiment. So overall, in this entire analysis, what number of type 1 errors am I going to commit within a set of comparisons? Okay, and your error rate per experiment is given as the product of alpha and the number of comparisons. Okay, so if alpha is 0.05 and I run 5 comparisons, right? What's my error rate per experiment? .25, so still less than 1, right? But I just reviewed a paper where they went through and did 120, 162, 164. Let's say 164 comparisons. Yeah, it's problematic. 0.05, 8.2. 8.2, a little over 8 of those are going to be, I would expect, just based on error rates, to just be type 1 errors, right? Just given the massive amount of tests that you've gone through and run, okay? And so what we want to do with our follow-up tests is we want to manage this family-wise error. Family-wise error reflects the probability of committing at least one type error across a series of comparisons, okay? And so what our series of comparisons, if I have 3 different ANOVA models, my family-wise error rate might be for this set, and for this set, right? And our family-wise error is given as 1 minus alpha to the C power, okay? So across 4 comparisons, let's say I have an ANOVA design, an ANOVA model, have 4 comparisons, each one of those tested at alpha equal 0.05. My family-wise error, without corrections, if we're not correcting anything, is 0.185, right? So it's getting close to a 20% chance that I've made at least one type 1 error within that whole set of comparisons. And this starts to become problematic. The more tests we run, the more likely it is that we're going to have committed at least one type 1 error. And so we want to go through and do something to correct that. So our family-wise error is going to be falling somewhere between our alpha level and the number of comparisons times our alpha level, or our error rate per experiment. But family-wise error and your family-wise error rate and your per comparison error, and your per error rate per experiment are going to be fairly close. Questions about sort of the problem, the issue that we're trying to address with this stuff? Okay, so general recommendations, and I hope you guys think about this when you're designing your studies, when you're analyzing your studies, when you're evaluating other people's studies. Be selective and only look at stuff that's meaningful, okay? If you have, and this starts to become more of an issue when we get into more complex factorial designs, you could have 30, 40 different possible comparisons. If we add repeated measures into the mix, yikes. There's 30, 40 different pairwise comparisons that you could take a look at. You probably don't need to look at all 20 or 40 some pairwise comparisons. Be selective, think about what's meaningful, why am I doing this, what are the effects that are of interest to this specific study, and then limit your tests to specifically those things that are important for your research, okay? If we're testing all possible comparisons, whether or not they're meaningful, I just went through and I ran all possible post hoc tests on all possible things. I'm gonna get a bunch of stuff that I don't care about, but I've tested it, and what I've done is I've wasted power, right? Now, if I'm correcting for everything, I just corrected for 15 tests when I'm only interested in 3. So what does that do to my threshold for claiming statistical significance on any one of those 3? Goes way up, right? Other thing that's going to happen is you might find stuff that is now statistically significant, and now you're locked into explaining it. Like, well, I don't know why those 2 things are different. It doesn't matter to anything I'm doing, but I've tested it, and I found it, so now I'm obligated to explain it. Ends up being a mess. And so what you should be doing is thinking about what's my family-wise error rate, and how am I going to go through and test this in a way that tests the specific comparisons that I'm interested in, and sort of gives a correction for sort of this limited set of tests that are of most relevance to the study that I'm running, okay? And you have to be careful about it, because SPSS isn't always going to do this, right? If you just ask for 2 key stuff, it's just going to it's going to correct for all possible comparisons. And when we get into factorial designs, a lot of times those comparisons aren't meaningful. You can't interpret them anyway, right? But you're still being taxed for those in terms of your threshold for statistical significance. So you want to be very careful as you're thinking about how am I going to go through and manage my follow-up tests. So again, just have a good reason for looking at those comparisons that you've got, right? I like this. I was saying the fact that you're able to do something rarely sufficient reason for actually doing it, right? I could look at all possible tests. Is that relevant? And so, like, can I justify the test that I've gone through and taken a look at? Yeah.
How is the number of your comparisons directly influencing power? Like, where's the connection?
Well, as you'll see in a moment, what I have to do is if I say I'm running 5 tests, right? And so my family-wise error rate is now way up, right? And what I want to do is get that back down to something that is about 0.05. So like the likelihood of me making a type 1 error across the set of comparisons is 0.05. So what ends up happening with my post hoc tests or the types of corrected tests, I increase the threshold, right? Now, functionally, it's not like our usual 0.05. Now I have to reach a much smaller p-value or a much more stringent criteria in order to claim statistical significance. And now, all of a sudden, if I've increased my, functionally reduced my alpha level for any individual comparison, what has that done to my power? It drops it down, it makes it harder, right? This thing that if I was looking at just one comparison on alpha 0.05, yeah, it's statistically significant. But if I'm correcting for 7 different comparisons, now all of a sudden it's not. It's p equals 0.03, but my new threshold for claiming statistical significance is 0.002, and so now rules say I have to say that we don't have evidence to claim that that's reliable effect. And so you'll see as we start to go through that our threshold for claiming statistical significance increases as we move forward with this stuff.
That's one of the reasons why we only look at, well, a lot of people only look at the ANOVA F before going into follow-up is this whole issue right here, is if you start running these tests without doing the F, you just have a ton of unneeded, unnecessary.
Yeah. And so having an F test that's an omnibus effect that's clearly not significant. Like it's not like, oh, it's a maybe thing. There's clearly nothing here. Cool. We can put that aside and move on to other things, right? I think the bigger concern is that without the F, people will then start mucking around and looking at various combinations of different types of things and say, oh, hey, look at this, and then make it a big deal about it. And so it's in part to keep people from screwing around and just playing with data and running all possible things until they find something that's significant, and then sort of pretending that that's what they were looking for all along. But it is, at the end of the day, another test that you have to run and probably should account for. And if I have very specific comparisons in mind, right? I'm doing this because I think this condition is going to exceed response relative to the combination of these 2 other conditions. This is why I'm running the whole damn study. This comparison right here. So I could care less about the omnibus test. What the omnibus test says, I'm going to test this I'm just going to ignore the ANOVAs because it's a waste of my time and not the purpose of the whole thing, right? But unfortunately, we often don't have that level of clarity when we're moving forward with stuff, although we should. Yeah.
So if you survey and you gather the things that you're looking for and you gather, let's say like demographic kind of stuff, and then you run your omnibus test and like it doesn't look like age or gender are really playing into anything, there's nothing significant there. You don't have to include those in your follow-up tests, and so even though they're in your original data, you can just not focus on those. Is that right?
I think it's into a methodological issue where it depends, right? This is what happens, right? Like I got, like, oh, and I find no difference across my groups in X, Y, and Z. Well, you got a group of 5 against a group of like 50. Of course you're not going to find it. Like not finding anything doesn't mean there's not a difference. It just means that your test isn't adequate or is sufficiently powered to find it, right? Other thing too is people are like, oh, I found a difference in gender on that, so now I'm going to control for gender. I don't know, does it make sense to control for gender? Does this mean anything? Is it something that you would expect, or is this just something that popped up in your data, right? And so with all of this, taking a much more planful and conceptual approach, just because you find a difference in groups on something doesn't mean you have to control for it. You could if you want to, if it makes sense, if you can give me an argument for why this is important. But people going through and saying, oh, well, we didn't find a difference in this, so we don't have to worry about it, is probably not accurate, right? If that's something that is relevant to sort of the construct of your area of research, you should probably still think about it anyway, right? And so these hard and fast rules of thumb, oh, you do this versus that, hopefully over the course of this semester and next, we'll try and divorce you from that. You should do what makes sense from a conceptual and scientific standpoint, not what you might have heard from your undergraduate class, or me, quite frankly. Like, because Josh said so is not a good excuse or rationale for anything outside of problem sets, right? But also not a good tact with your advisor. Like, don't tell your advisor that, like, I told you that I had to do something when you're running analysis. So, like, listen to your advisor, do what your advisor says. Then I've got colleagues coming up to me and sort of upset with me because I apparently told their student that they had to do something or not do something. So, I mean, all of this, there's no hard and fast rule. I mean, there's general principles and things along those lines, right? But you should, you should have a good reason for doing anything that you're doing. You should be able to justify it. You should say, this is why I did what I did, right? Given X, Y, and Z, this is the approach that made sense. Yes, there are 7 other ways I could have done it. This is the reason I didn't do it that way. This is a part of the reason, like when I'm having you guys calculate effect sizes, there's 3 or 4 different ways to do it. Tell me why you did it, right? Give me a rationale. I just don't want you to plug and play stuff and sort of automating through things without thinking about why you're doing it. Okay? Other questions about this? All right. Going back to my favorite article, Wilkinson. Researchers rarely need to compare all possible means to understand the results or to assess their theory. By setting sites large, they sacrifice power to see small. Lattice of all possible pairs is a straitjacket. Forcing themselves to wear it often restricts researchers to uninteresting hypotheses and induces them to ignore more fruitful ones. If a specific contrast interests you, examine it. If all interests you, ask yourself why. Okay? Again, we don't do a good job. We're just like, I don't know, we'll just see if there's stuff going on there. That's not a good way to conduct science. Okay? And if you just decide to go through and do all possible comparisons, like I said, now you're obligated to explain any type of effects that you find. And if you're, depending on how many in there, a couple weird ones are going to pop up that aren't going to make any sense. But now you have to explain it because you tested it. Impetus is on you to explain what you've done, right? So instead of focusing on the 3 tests that I did the whole experiment for and telling my story around that, now I've got 7 different things I have to talk about, and everything's a mess. And I don't have a clean story because I went through and looked at a ton of stuff, and I ended up having weird things pop up. So, and this is going to happen. I'm going to have you doing a set where you run post-hoc tests and then have to explain to me what all those things mean. It's aversive. It's not going to be fun. But in part, I mean, just to give you practice and exam, but hopefully you start to see that, like, oh yeah, boy, if I just run everything, now I have to talk about everything, and that can get taxing to go through and have to talk about everything, right? So just be very, very careful as you're going through and approaching how you're gonna go through and test some of these things, okay? So, think about a priori versus, and the purpose of that assignment isn't to give you a headache and make things tedious. It's to give you practice with approach to post hoc tests, but it can be tough because now I've got like 7 different things to account for that are kind of related but not really, and now I have to think about different stuff. It ended up being a lot. So if we're thinking about follow-up tests, right, we want to distinguish a priori tests from post hoc tests. Our a priori comparisons, these are theoretically meaningful comparisons. These are things, hopefully, that we've developed before we even run the study. This is what's great about theses and dissertations, right? You're creating a study, and you're saying, this is specifically what I'm going to look at. We say, sounds good, then you go forward, and you have this set of comparisons that are your specific reasons for going through and doing that. There may be other things you could test, but you're saying, these are the things I've called my shot before I even ran the study. We will, within an ANOVA model, a one-way ANOVA model, we're going to evaluate our a priori comparisons with the series of linear contrasts or potentially independent sample t-tests. And typically what we do is we conduct a priori contrasts at per comparison error rates. Okay? The idea is that you've called your shot before we started this whole thing. You're not mucking around. You're not fishing for things. You've said, Nick says before he runs his thesis, I'm running an ANOVA model, and I'm expecting these 2 groups to be different than this group, and I'm expecting this one to differ from that one, okay? And from a theory-based standpoint, that's the whole reason, the whole rationale for doing this study. And if you've called your shot, before you do that, you don't need to, the convention says you don't need to correct for those things and sort of reduce the power of those tests because you called it before we even set things up, okay? Now, some will argue for some correction using a Bonferroni or Dunsittic, particularly if we have, if I have 9 a priori comparisons that I've made, then that starts to get problematic, right? But again, thinking about having a small set, like these are my specific comparisons, like these are the heart and soul of my study. I might go through and do other comparisons that I then go correct for, some post hoc stuff, just kind of an exploratory thing, but these are the heart and soul of the study, and so with these ones I can test these a priori comparisons at per comparison error rates. Because again, as we start adding corrections, it makes it harder and harder to find statistical significance. Our post hoc comparisons, oftentimes this will be an analysis of all possible pairwise comparisons, and generally this happens after we've looked at the means. If we've run the study, we're like, oh, I wonder if this group is different from that group. We're like, oh, that's kind of interesting. I wouldn't, but no, that kind of makes sense. I can see how maybe these 2 things would be different. We've got now other things that are going into our error rates outside of just sort of the number of tests that we run. For our post hoc comparisons, these are, there are a number of different procedures we can go through to correct for these types of exploratory analyses. Easy to get these in SPSS. You just go through and check boxes. I want X, Y, Z, and we'll walk through those. Okay, but note, as I said before, limited number of planned comparisons is always going to be the theoretically more defensible approach. Okay, this is the reason I'm looking at these things. If you want to look at those things, their means and standard deviations, go nuts. You can test it on your own. But this is the reason I'm going through and doing these comparisons from my study. So again, our rationale, if you really do need to look at all pairwise comparisons, you should have an equally compelling, if not more compelling rationale for why you really need to look at all possible pairwise comparisons within this set, okay? Arguably, from a methodological standpoint, the threshold for running 1 billion post hoc tests should be much, much higher than the threshold for saying, hey, I've got 5 different means, but these 3 are really the ones of this specific set is really what I'm going to go through and take a look at, because that's what's most important in my research question. Questions on this? All right, so planned comparisons. From a classical standpoint, if I'm wanting to do just a pairwise comparison between 2 means, right? I've got 4 levels to my ANOVA, or 4 levels to my factor, but I want to compare 1 and 2 and 3 and 4, okay? So we're just working with 2 means. Traditional way to approach this. And this is going to be in situations where we have equal cells, relatively equal cells, and equal variances, so we don't have a violation of homogeneity of variance. What I'm going to do is I'm going to calculate a t-statistic. My t-statistic is just going to be the difference between my two means of interest and of a table divided by the size of my first sample plus the mean squared error divided by the sample size of my other sample. Okay? So again, what we're doing here is we're capitalizing. So do we have, where do I have a more precise estimate? When I have a larger sample or a smaller sample? A larger sample, right? The idea behind this is if we've run an appropriate ANOVA model, we haven't violated assumptions. We're saying that the variance in population 1, and the variance in population 2, and the variance in population 3, the variance in population 4 is what? The same, right? So does it really matter if the population variances are all the same? Does it really matter which variance I'm looking at, or which one I'm looking at? No. And so our mean squared error, remember, in our ANOVA table is like a pooled error estimate. And if I don't have evidence of differences in my variances across my different groups, what I can do is just substitute my mean squared error as like a pooled variance estimate, right? I'm just going to drop mean squared error from my ANOVA table in, divide that by the size of my first sample, take it again, divide by the size of my second sample, take the square root of that. That's my t-test for comparison, follow-up test for ANOVA. My critical value, and this is important, is going to be my t with my alpha level divided by 2, so a two-tailed test here, for degrees of freedom error from my ANOVA table. Okay. So this is our traditional approach to pairwise follow-up tests in ANOVA, and the use of our mean squared error and corresponding degrees of freedom gives us a much more, well, it depends on how much more, but it ends up giving us a more powerful test of our specific contrast. Why is this? Why is our test going to be more powerful if I'm pulling values out of my ANOVA table as opposed to just running a independent sample t-test like I would otherwise?
So it's already corrected for your errors, hasn't it?
Okay, so yeah, my mean squared error is going to be a more precise estimate, okay? What about my degrees of freedom? How do I calculate my degrees of freedom? Or where do I get my degrees of freedom error from?
The sample size.
Yeah, and what sample size? You're right.
Yeah, the mean.
My
sample
entire
is-
sample, right?
Yeah.
So if I've got a test, and I've got 4 levels of my dependent, or to my IV, right? And I've got 20 people in each cell, right? What's the degrees of freedom I'd be looking at if I'm just comparing sample 1 and sample 2 with an independent sample t-test?
That's sum minus 2,
Yeah, and so 20 plus 20 minus 2?
38.
38, right? Well, what if, what's my degrees of freedom for my overall ANOVA table?
Your total sum minus how many groups you have.
Yeah, and so what's that going to be? 20 per group, and I got 4 groups.
80 minus 4, so 76.
Okay, and if I'm running a critical test with 38 degrees of freedom versus 76 degrees of freedom, which one of those is giving me the more advantageous critical value for my purposes? The higher degrees of freedom, right? And so the idea is we've gone through and we've got 4 different populations with different means somewhere, but equal variances, right? And so what we're going to do, if all these populations, if each one of the populations has an equal variance, then my mean squared error is a nice aggregate, is probably a really nice estimate of the what the variance is across these different groups. And so we've got a more precise estimate of our error. And what we're also going to do is going to capitalize on our design and say, well, we've got not just a pairwise test, we've got a lot. And so basically what we're going to do is we're going to plug in degrees of freedom error from our overall ANOVA, which is going to give us a more powerful test because it's going to reduce the critical value that we're going to be going through and have to use here. Okay. So people see why this is advantageous, how we're capitalizing on our design here in the pairwise test. Okay. But the whole premise of this is that we've got a good design. We've got relatively equal cell sizes. We've got no problems or concerns with homogeneity of variance, right? And so we get rewarded with this. HAL does a nice job of saying, well, this isn't always the case. Sometimes we don't have equal cells, and sometimes we don't we have violations of homogeneity of variance. If that's true, then all of a sudden I start to question whether or not that's a good estimate of error, right? Because this is like a pooled error variance for a bunch of populations, but the assumption is those populations have equal variance. If they're not, right, and group 4 has a way, way bigger variance and a way bigger sample than groups 2 and 3, but my interest is comparing groups 2 and 3, now I've got an error estimate that's saturated with group 4. Group 4 is not involved in this, and so now it's going to be way bigger or way smaller than what I would expect within these two populations, and things start to get complicated, right? And so, if we have unequal cells, unequal variances, t-test using pooled variance, Welch-Satterthwaite correction is probably your better option here, okay? We had an opportunity to capitalize on our design if we didn't violate assumptions, but we have, and so now it's probably not appropriate. I have less confidence that this is going to give me an accurate test. Probably what I need to do is be conservative and just go through and run my t-tests as I normally would as a follow-up instead of pulling terms from my ANOVA model. Okay. Questions on this? Okay, people comfortable with this? So that's a nice t-test formula. The t-test formula should be giving you warm fuzzies at this point. It's something familiar, right? Our follow-up tests, our post hocs, our contrasts are just the same thing. They're just a different version of this. It's not different in any way, shape, or form. It's the same formula. We're just tweaking what goes into it. Okay. All right. So planned contrast, if we're just running our independent sample T, we would go through, we would run our ANOVA design, find that we have an omnibus effect, and then we say, okay, what we're going to do is we're going to go down through and we're just going to run independent sample t-test. So here, what I might do is I might say, I'm looking at emotional arousal, but in SPSS what I can do is I can say, my grouping variable is going to be ethnicity. Now I've got 4 levels to ethnicity. What I can do is that when I hit define groups, I can go in there and say, all right, well, I'm specifically want to look at groups coded 0 and 1, okay? So even though you have a categorical factor with multiple levels in your t-test, right, you just go down through and tell it which levels you're wanting to compare, okay? And so again, in the 2 comparison case, so if I'm just looking at two tests, my family-wise error rate is just 2 times 0.05, right? If both the null hypotheses are true, right? So again, that's not too bad, right? I've got an ANOVA, I've got 2 follow-up tests. I can just run this. I mean, my error rate's not going through the roof. And if I plan these out on the front end, I'm probably okay saying, just gonna go through and compare these at per comparison error rates. Okay. Questions up to this point? All right. Now we're getting into the big stuff here. Linear contrasts, okay? Our linear contrast, so let's say, okay, we've got, so I want to compare this group, that group, that's fine. But let's say I have hypotheses that are a little bit more complex. Emilio's running a study and he's like, well, I've got this control group, and then I've got 2 experimental groups. But my thought is that individually, these 2 control groups would be different than, or these 2 experimental groups would be different than the control group. But I'm even going to so get a little more elaborate. I'm going to say the combination of these 2 control groups together exceed, or these 2 experimental groups together exceed my control group. And so what I want to do is I want to look at the comparison of controls versus the combination of these 2 groups. Now we run into a problem because it's hard to do that with just our independent sample t-test because they're 3 different groups, right? This is where a linear contrast comes in. Provides us with a more flexible approach to testing the specific hypotheses that we have. What we're doing is it's a generalization of the t-test. We're still looking at differences between combinations, 2 different combinations of groups, where we can start to mix and match what conditions and what groups go into each other to start to come up with more meaningful, oftentimes, and more efficient comparisons to make. So, linear contrast is just all we're doing with our linear contrast is we're just specifying a linear combination of means, okay? So here, this is our linear contrast L, we've got weighted mean 1, weighted mean 2, weighted mean 3, so on and so forth. We can note this more efficiently as just the sum of our weights multiplied by our means. And so, all we're doing is we're just saying that, so here are the means that we have in our study, and we're just weighting these, right? So if we assign all of our A values, if we just assigned all of our weights to equal 1, this would just be a sum of our means, right? Wouldn't be necessarily useful for much, but that's what it would be, okay? So if each one of these A weights was 1, we get our value for L by just adding up all our means, right? If, however, we set our weight to 1 divided by the number of groups, so let's say I have 5 levels to my factor, right? So I've got 5 different groups. If I set my weights to 1/5, so I have 1/5 times mean 1, 1/5 times mean 2, 1/5 times mean 3, so on and so forth. What I end up with is the mean of all group means, right? So basically, I've summed everything together, divided it by 5, right? Okay. So this is just a general linear contrast here. What starts to become more effective if we specify a linear contrast, indicated by our psi symbol here. When we specify a linear contrast where the sum of our weights equals 0, this is something that we can start to use to start testing specific hypotheses, okay? So let's say we've got 3 means, x1, x2, x3, okay? So we run an ANOVA, which has got 3 factors, right? And what I do is I assign weight to mean 1 of 1, a weight to mean 2 of -1, and a weight to mean 3 of equal to 0, okay? If I add 1 plus -1 plus 0, my weights sum to 0. This is gonna tell me that I've created a linear contrast. Okay? And if I go through and I write this out, okay, so the value of my contrast is gonna be 1 times mean 1 plus -1 times mean 2 plus 0 times mean 3. What have I got? What have I just done?
You made your answer 0.
Well, no, because these are gonna be some values. So this is some mean value for my groups. What am I comparing here? Perfect. Mean 1 and mean 2, right? Basically, 0 times anything makes that go away. Basically, I've got mean 1 minus mean 2. The set of weights that I've set up has created a difference, allowed me to look at the difference between group 1 and group 2. So let's say, instead of 1, -1, and 0, let's say I set my weights for group A to be 1/2, group 2 to be group 2 to be 1/2, and group 3 to be -1. Okay. So if I put that out, I've got 1/2 plus 1/2 minus 1. Nick, what am I doing here?
So basically, adding mean 1 and 2, dividing those in half.
Yeah.
And then you're subtracting mean 3.
Yeah. So, perfect, right? So basically what I'm doing is I'm looking at the combination of group 1 and 2 and comparing that against group 3. Basically, this is a contrast. What I'm saying is the combination of groups 1 and 2 different in mean than the combination, or than in group 3, right? And so what I can start to do, again, if we add 1/2 and 1/2 and -1, and we sum these up, we get 0. We've got a linear contrast, right? But what this does functionally for us is it allows us to start creating comparisons of groups of interest by assigning certain weights. So basically, I'm just taking the average of groups 1 and 2, and I'm comparing that against group 3. People see how this is coming?
Can you reverse it and do it with any of the groups?
Yep. And we're going to go through and do this, right? So if you're going to go through, so this was where, who's been presented with like contrast coding stuff and had to do this stuff previously? Yeah. it's kind of intimidating, right? And it's kind of complicated. And if you want to get in the nuts and bolts of this, if you want to get into like tight experimental design and orthogonal contrast and things like that, then it gets deep, right? We're not going to worry about that necessarily. What I want you to understand is how we go through and start to set up contrast that look specifically at the types of comparisons that we're interested in taking a look at. But the very first thing we need to do is we need to go through it and figure out how are we going to assign our weights, right? So if you want to select your coefficients or your weight coefficients here, first thing you want to do, identify the treatments that you want to compare, right? Which groups do I want to be involved in this comparison, okay? Do that. Then what you want to do is you want to assign weights as the reciprocal of the number of treatments in the set. Okay, reciprocal just means the inverse, right? So if I got 3 groups in this set, what's my weight? 1/3. If I got 5 means in this group, what's my weight? If I got 1 group in this comparison, what's the weight? 1, right? If this group isn't in the comparison, what weight does it get?
It's not in the.
Yeah. What weight do I assign it?
1.
What? 0, right? 0 makes it go away. Because I multiply 0 by anything, it just disappears, right? And then what I do is I assign one of the sets of coefficients to be negative, right? When you're doing this is arbitrary, doesn't matter. But generally what's going to be beneficial is if you're assigning a specific contrast, you're assuming that one group is going to be higher than the other group. And so which group gets the negative sign? The lower one, right? So let's say I've got 5 means, x1 to x5. And I want to say, is the combination of groups 1 and 2 different from the combination of 3, 4, and 5? Okay? So I've gone through and I've decided these are the groups that I'm interested in. 1 and 2 against 3, 4, and 5. Okay? What do I assign my weights as? What do I assign my weights for this group to be?
Which one do you expect to be higher?
Let's say this one.
Would be half, then negative 1/3, 1/3, 1/3.
Yeah. So we've got 2 groups in this, so I'm going to assign weights of 1/2 to each one of these. We've got 3 means here, I'm going to go 1/3, 1/3, 1/3. Right? If I expect 1 and 2, the combination of 1 and 2 to be a higher mean than the combination of 3, 4, and 5, I'll go ahead and assign negatives to this. And if I add 1/2 and 1/2 plus 1/3 plus 1/3, or sort of minus 1/3 minus 1/3, I get 0. This tells me that I've specified a linear set. Okay, always do this. Once you go through and assign weights to your groups, add them all up and make sure that they sum to 0. If they don't, you've made an error somewhere. Okay, so functionally, I'm going to go through the sum of my weighted means is going to be 1/2 times x1 plus x2 minus 1/3 plus x3, 4, and 5. Basically, I'm just taking, if we look at this, I'm just taking the average of the first 2 groups and subtracting the average of the next 3 groups. That's functionally all I'm doing. Okay. So in practice, it's pretty straightforward. You just need to make sure that your weights are assigned so that they're doing what you think they're doing. Okay. So, people have questions? See how we did this? All right. So we know that we have a set of linear coefficients if we add up our coefficients and they equal 0. Okay. But if we find that our coefficients, if we add up the absolute values of our coefficients, and those sum to 2, what we have is a standard set. Absolute value is just sort of dropping the sign, whether it's positive, negative, making everything positive. So if we take 1/2 plus 1/2 plus 1/3 plus 1/3 plus 1/3, we get a value of 2. That means we have a standard set, and this starts to become important for going through calculating our effect sizes, because literally what we have is the combination of the average of the first 2 means and the average of the second 2 means. Okay. So now, Emilio, is this if I want to compare mean 1 and mean 2 against the combination of 3, 4, and 5, are there other weights that I could assign here?
Not to equal 2, no. Not to equal 1 and 1. I mean, you can put it at any. I mean, you can make it equal 2 and 2, 2 and -2, 3 and -3.
Exactly. Okay. These are the weights we need to create a standard set. But if we just want a linear set of contrasts, right? what if I say, I'm gonna weight mean 1 is equal to 3, this one equal to 3, and that's 2, -2, -2, -2. Is that a linear set? Yeah, right?
Is it still equals 0?
Yep, 3 plus 3 minus 2 minus 2 minus 2 is still equal to 0, right? That's perfectly fine. I can do this, and my statistical test is still gonna be accurate, okay? The problem is I've taken, so now the value of the contrast that I get isn't gonna be in the scale of my original values, and so it's not gonna be immediately interpretable. But, as we'll see if I'm working through SPSS, SPSS is gonna check you when you're specifying your contrast, to make sure the sum of your contrast is 0. 3 is a repeating decimal. I can't take that into infinity in SPSS. I'm going to have to like put 0.333, and that's where it's going to start doing it. If I go 1/2 plus 1/2 minus 0.333 minus 0.333 minus 0.333, do I get 0? No, not quite, right? It's going to flag that. So if I want to get precise in terms of my statistical test, I can tell SPSS, well, I want this to be 3 and 3, -2, -2, -2. Those are whole numbers. It'll do that. My statistical test will be the same as it would be if I would have done this. It's the only thing that I have to worry about is now the value of my contrast isn't a literal representation of the difference between the mean of these two groups and the mean of these three groups. Yeah.
Is there a situation where we would want a linear set over a standard set?
No. Your standard set is going to be any standard set you have is going to be a linear set.
Okay.
Okay.
But if the values don't sum to, then it's something else, or is it always going to sum to?
If the values sum to something that's not 0, then you've got something different that's not useful for our purposes here.
If you have to change it, that's just software related, you're saying. I mean, basically software related, why you would make it not a standard set. So is there an easy correction for that, or?
Well, I mean, you've got 1/2, 1/2, 1/3, 1/3, 1/3, right? I mean, if we can just take this and make this 3 and 3 and 2 and 2 and 2.
Right, I mean, but to take it then and make it standardized again.
Oh, you just do that by hand if you wanted
Okay.
to, yeah.
Functionally, what's different between these linear other than the summing to 1 and the standard set between linear contrasts and linear regressions? Because I mean, linear regressions give you that weight. They're not, 1/2, just whatever.
Yeah. That's a different thing. We're getting those weights.
Yeah, but couldn't
differently.
you compare the weights within that linear regression similar
We
to
can,
this?
if you're working with categorical variables,
Yeah.
you can, again, like we talked about before, anything that you're doing in an ANOVA model, you can do in a regression
Yeah.
model, right? And so we can go through and do this. So I wouldn't get confused or turned around about sort of thinking about this as equivalent to a linear regression, but in terms of like a linear function, yeah, it's sort of working on sort of the same types of principles. All right, so this all works fine unless I have dramatically different cell sizes, and then this starts to screw with the hand calculation of our contrast. So in general, when we're working through and doing hand calculations with these, we want cell sizes to be relatively equal. If they are not equal, then things start to get thrown off. But sort of just note this again, this issue about having a balanced design, it's not a formal assumption, but it just makes things work out much easier. And so wanted to keep that in mind when you're running stuff. So we know how to calculate set our weights so that we can get specific contrast that we're interested in. Now our classic test of this. Now don't worry, I want to present this to you just so you know what it is and how it looks like. So if you run into it later, you're not confused about what's going on. But the classic approach to running our linear contrast is going to be to calculate an F-test for a linear for these contrasts. So what you would do is you would say the sum of squares of the linear contrast is you derive this from treatment means and associated weights. So we have our linear contrast that we specified, right? So this is our linear contrast, right? So we go through and we get the value of our contrast here. So then what we would do in our classic approach is we would take, once we've got the value of our contrast, right? Then we take and calculate a sum of squares contrast where we take the sample size, the cell size, assuming an equal number of individuals times the square of our contrast over the sum of my squared weights, okay? If I have unequal ends, I'm creating the sum of squares contrast as the square of my, the square of my value, my contrast, over the sum of the square of the weights over sort of individual sample sizes here, or cell sizes. What I would then do, okay, so let's say we've got 10 people per cell. I've got x equals 1.5, x equals 2, x equals 3. I'm going to say weight 1 is 1/2, weight 2 is 1/2, and weight 3 is -1. Kate, what am I comparing with this set of weights?
We're comparing the average of
Yeah.
the average of the first two with the
Yeah.
third one.
My contrast here, what I'm interested in is comparing the combination of the first two with the second, right? So I go through and I calculate the value of my contrast, which is going to be 1/2 times 1.5 plus 1/2 times 2 plus -1 times 3. Going to give me a value of my contrast of -1.25. Okay. Haley, do I have a linear set here, or excuse me, do I have a standard set here?
Yeah.
Yeah, right? Because if I take 1/2 plus 1, I get 2. I've got a standard set. So I know I can interpret the value of my contrast as the literal difference in my units in terms of the average of groups 1 and 2 versus group 3, right? Based on the value, the calculation of my contrast here, I'm saying that the combination of groups 1 and 2 is 1.25 points lower than my group 3. Okay. People understand this? Okay. So then what I would do to calculate my sum of squares contrast is I would take -1.25, so I take n, the size of each one of my cells, times -1.25 squared over, again, the sum of my squared weights. So I'd take 1/2 squared plus 1/2 squared plus -1 squared. I would go through, and this would give me my sum of squares contrast. And then what I would do, because our linear contrast is 1 degree of freedom test, right? I'm just comparing two different groups. Now, the one group is a combination of groups, but literally it's just I've created two different groups. My sum of squares contrast is equal to my mean squared contrast. And because I'm basing all this from my ANOVA test, in order to calculate a statistical test for this, what I would do is I would calculate an F statistic where I take my mean squared contrast, which is just the same thing as my sum of squares contrast that I've just calculated, and divide this by the mean squared error from our overall ANOVA table. Okay. And then what I would do is I would take my test statistic here, and I would compare it against a critical value for F of 1 and whatever the degrees of freedom error is from my ANOVA table. Okay. So this is the classic approach to sort of F tests for your linear contrasts. But there's a lot of stuff kind of going on in this, and there's some issues with my cell size has to be equal for the calculation of, things start to get screwed around if I don't have identical cell sizes and things along those lines. And so what we're going to do in this class is we're going to work with not with an F test, but with a T test. And this is what SPSS is going through, and it's calculating your contrasts. Test of our linear contrast in SPSS is going to be given as a T. And our T test is just going to be equal to the value of our contrast over a standard error estimate. Okay? So again, we're calculating the value of our contrast. And then once we have our contrast, think about the value of your contrast is that's just like the difference in means that you would see and run in any other T statistic. Right? Then what we're going to do is we're going to calculate a standard error estimate. Standard error estimate is going to just be the square root of our mean squared error from our ANOVA table times the sum of my squared weights over the individual sample sizes. Okay. So this kind of simplifies things and makes things sort of fall more into line with the way we've been calculating test statistics before. Our T critical is just going to be our alpha level to divide by 2, sort of our two-tailed test with degrees of freedom associated with our mean squared error or degrees of freedom error here, right? And for a balanced design, our F and our T calculations are going to be identical. They're going to be the exact same in a balanced design. Again, someone remind me, what's the relation between F and T for a 1 degree of freedom test? What's that?
And they're the same.
Yeah, they're the same. How do I go from an F to a T? Yeah. I take if I take the square root of my F, that just gives me a T statistic. If I take my T and I square it, I get an F. Okay. So if I were to be looking at two groups, right, and I could run an independent sample t-test, and I get the t statistic for my t-test for that test, if I were to go through and take the same two groups and run them in an ANOVA model, which I could do, right, I could run it through a one-way ANOVA model, and I would get an F test for those two groups. Those are going to be they're going to be a direct association between my t is just going to be the square root of my F, right, or the square of my t is going to be equal to the F. Go back and forth with this. Okay. Now, SPSS is also going to provide a corrected test, standard errors, if we violated homogeneity of variance. Okay, this is one of the nice things about SPSS. I'd have to do some digging and figure out how it's doing it. I'm not 100% confident that how they're doing this and presenting this is something that people agree on is a good correction for this, but they report it, and so I don't know. But basically, when you look at SPSS, and it's going to give you contrasts, assuming equal variances and not assuming equal variances. For the not assuming equal variances, we've got a correction to our standard error estimate, where our standard error is going to be the square root of the sum of my squared weight times the variance of my group, each one of my groups, over the sample size of the group. Take that squared. And then I'm going to have a corrected degrees of freedom test, where we're going to take the sum of my squared weights times the variance of a group divided by the size of the group, do that for all of my weights, square that over the sum of sort of this business down here. Basically, we're just getting a corrected degrees of freedom test for this. My test statistic is just, once again, going to be the value of my contrast over my modified standard error estimate. My T critical is just going to be my T for my two-tailed test for my corrected degrees of freedom here. Okay, and if you want to get corrected degrees of freedom, the t-value calculator that we use sometimes won't handle, this will often be a decimal place. So you'll have degrees of freedom are 23.476 whatever. If I try and get a critical value for t with 23.476 degrees of freedom, it won't give it to me. It will only do whole value numbers for degrees of freedom. This calculator right here will give you specific degrees of freedom for a specific critical value for tests with sort of a degree of freedom that go to some sort of decimal place here.
I have a quick question.
Yeah.
Can you remind me again how the F statistic is reported? So like in the article and the problem set, they gave F statistics, and I just want to make sure I'm interpreting that correctly.
Okay. What is the interpretation of it for an omnibus test?
I don't know.
So what F do you want to interpret?
Well, I think if you go back one and you listed, I think it's listed as with the degrees of freedom error.
Yeah. So this F test is just still looking at a pairwise comparison, right? Because I can run a pairwise. Any t-test that I run,
right?
Independent sample t-test, I can run an ANOVA and get an F for it, and it just means the same thing. If I'm only comparing, think about this. So in an overall ANOVA model, right? So I've got, like, say, 4 levels to my independent variable, right? And I get a significant F. What does that tell me?
That somewhere in those 4 levels there's
Just somewhere in there, there's a difference, right? What if I have only 2 levels? What does that tell me?
That there is a difference.
Yeah,
between
right.
those two.
It still tells me somewhere in there there's a difference, but there's only 2
options.
So I know what that there's a difference, right?
Okay.
I don't need to run a follow-up test with that because I already know that these two things are different, right? So, yeah, say it means the same type of, it means the same thing. If I'm running an F with only two groups, then it's not really an omnibus test, it's a specific test of that. I'm just using a different test statistic.
F instead of T.
Yeah.
And it's reported as the F value and the degrees of freedom.
Yep.
Okay.
Yep. Okay. Other questions on this? All right. So, managing our family-wise error for our planned comparisons. Again, typically the classic approach to this is to look at our pairwise comparisons at per comparison error rates. Okay. If I've called my shots ahead of time, I get some extra leeway, and I'm just going to go through and look at and set my critical value equal to alpha 0.05. Okay. But some people will, depending on how many a priori comparisons that you have, some concerns about looking at all of those at per comparison error rates. So for example, if I have 4 contrasts, my family-wise error starts to get close to 0.2 if all the null hypotheses were true, right? Like, so literally none of these predictions that I've made are accurate. If that's the case, there's likely a 20% chance that at least one of those will come up as statistically significant. So some people will argue, like, yeah, even though you called your shot before, you should still think about making some corrections. Some things that we can start to do if we have, say, 15 a priori comparisons, you should maybe think about, like, do I need all of those? Like, are all of these crucial comparisons that I need to be testing, right? And if not, we can start to pare down sort of our specific tests we're going to do. Or the other thing we can do is set a more stringent level for our family-wise error, right? We can bring that down. A couple of ways we can do this for a priori comparisons. We can use Bonferroni test, okay? Our Bonferroni is given as our corrected p-value for Bonferroni, alpha prime, is going to be our alpha level divided by the number of comparisons, okay? Bonferroni is really, really easy. We just take, so what's my alpha level? 0.05, and I have 4 tests. What's my new p-value I'm shooting for? What do we got, Kate?
0.0125.
Okay, 0.0125. All right. I've had confusion in this before. I hadn't anticipated it, but now I anticipate it now. All you need to do is you need to just run your statistical test. It's just the p-value that you're looking for is 0.0125. That's your new threshold. Your new threshold with Bonferroni, like, you're not impacted, you're not changing your statistical test. You're not changing how you're calculating your t's. You're not changing your critical values. You're not doing any of that stuff. All you're doing is you're just getting your p-value for your test and just seeing whether or not that p-value is less than 0.0125. Okay, so people have done weird stuff trying to correct it, critical values and things along. No, don't do that. Don't do that. If you have a Bonferroni correction, run your stuff. If you run it at SPSS, then you just got your p-value, and then you just look at your p-value. If you're doing it by hand, run your test, get your p-value, and then all you need to do is compare your p-value that you got against your Bonferroni corrected p-value and see, is my p-value lower than my corrected Bonferroni? Just like you would before, it's just your new threshold isn't 0.05, it's something different. Okay. So this whole approach is based on the assumption, or the mathematical proof that probability of one or more events never exceed the sum of individual probabilities, right? So if I have a probability, if my per comparison error rate is 0.05, probability of at least one type error, one type 1 error across these 3 independent tests is now 0.15, right? So what we're going to do is we're now going to go through and we'll correct that alpha level to go through and bring that closer down. So my per comparison error rate is now no longer 0.05. My per comparison error rate is 0.0125, and so if I add all of those up, my overall comparison or error rate for the whole set of tests is now equal to 0.05 like it was before. And I can't express this enough. Bonferroni is appropriate for correction of a small number of planned contrasts. Do not Bonferroni correct for a bunch of post hoc comparison tests. Like I've got 15 tests. I went through Bonferroni corrected that. I had sort of Bonferroni corrected for all the correlations in this matrix. Like Jesus, don't. Like that's not what that's for. Bonferroni is nice because it's easy to apply. Like how many tests do I have? I just divide my alpha by that, and that's my new p-value that I got to reach. But it's going to be too much of a correction. It's going to be too severe of a penalty for a large amount of tests. For a small test, if I've got say 4 or 5 a priori tests and I want to correct for those, this can be an appropriate test here. Say 3 or 4 tests, and I just want to be a little bit more conservative. This is where we should be using this. This is not a post hoc correction. You should not Bonferroni correct for a ton of pairwise comparisons because you're just gonna, that's way too much. It's way too heavy in terms of a correction. Other option that we have, similar to Bonferroni, we call this a Duncitic. Here we're gonna change our alpha prime a little bit. Instead of just taking our alpha level and dividing it by our number of comparisons, here we're going to take 1 minus our alpha level, and we're going to take that to 1 over the number of our comparisons. Okay. So if I have, if I'm running 4 comparisons, my Bonferroni correction, my new Bonferroni value for P that I'm looking for is 0.0125. If I run the Duncitic, right? So again, I'm running 4 comparisons, right? I'm going to take 1, and I'm going to take 1 minus 0.05, and I'm going to take 1 minus 0.05, and I'm going to take that to 1 divided by C is going to be 0.25. I'm going to take 1 minus 0.05 to the 0.25 power. What do people get for their Duncitic? Yeah, 0.0127, right? So it's very close to the Bonferroni. It's just a little bit more precise, right? I mean, we've got like a difference of 2 10,000ths on your P, but again, a different approach you can take.
And is that more appropriate if you had like 11?
No,
No.
neither one of these.
Neither of these is.
Neither one of these.
Okay.
We've got other tests that we can do if you got 11. If you have just a purely exploratory setting, which is fine, right? I just want to see what's going on. Like no one's ever looked at this before, so I've got questions, and so I'm just planning to have a bunch of tests just to see what's going on. Thinking this is a study for hypothesis generation, things along those lines. There are different approaches we can take, but these two aren't going to be one of them. Okay. Okay. Confidence intervals for our contrasts. This is going to be pretty straightforward. It's the same type of formula that we've used before. Confidence interval is going to be for our pairwise effects, right? It's just going to be mean 1 minus mean 2 plus or minus t times whatever, our critical value times whatever we've used as our standard error estimate, right? Whatever we use as a standard error for our test statistic, that's the same standard error we're going to plug into here. For our contrasts, we're just going to take the value of our contrast plus or minus of our critical value for a two-tailed test times, again, whatever standard error estimate we used for our test there. Our effect size, some differences that we can have here, okay? For our D, for our pairwise test, we can take D as x1 minus x2 over our pooled variance estimate, right? Just like we would before. For our linear contrast, we can calculate D as the value of our contrast over some standard deviation that represents within group error, okay? Now what this is can depend on a lot of different things. We can plug in down here the square root of my mean squared error, okay? Again, remember that your mean squared error is just your pooled variance across all of your different cells, right? And if I haven't violated my homogeneity of variance assumption, what does that tell me that, what does that suggest about the populations, the variance of the populations from which these samples were drawn, Laura?
They're all the same.
They're all the same. So this pooled error variance across all my different cells is probably a pretty good estimate for the variability within groups of any group that I'm looking at, right? So cool, right? If I've got a relatively balanced design, I haven't violated homogeneity of variance, mean squared error, that's a nice, just sort of within group error estimate that we can take, and it's probably going to be more precise than my estimate of variance within any individual group, because this is going to be based on everybody in the design, right? But I could also go through and calculate my standardizer here as the square root of the average variances of the sample in questions, right? So again, if I have a balanced design, but I have violation of homogeneity of variance, right? And I'm sort of looking at these three groups, and this group isn't in my contrast, but this group has a wildly different variance. I might not want to just pull my mean squared error out of it, because that's going to increase or decrease my variance estimate inappropriately, right? So what I'm going to do is I'm just going to look at this my standardizer is the square root of the average variances across my groups, assuming that I have equal cell sizes, okay? Because that's going to say, well, what I'm going to use as my standardizer is just the average variability of groups that are in my specific contrast here. Or what I can do is I could take maybe, so I don't have equal sample sizes though. Maybe I have unequal variances and unequal sample sizes. So now I want to go through and have some corrections here. And so what I could do is I can take the square root of the pooled variances of the sample in questions. This is just going to be a modification of your pooled variance estimate, right? So if I go through and I've got pooled is n1 minus 1 times variance 1 plus n2 minus 1 times the second variance. But what if I have 3 or 4 groups that I'm needing to pull together? What do I do now?
Keep going.
Yeah, just keep going, right? So I go, okay, so the sample size of group 3 minus 1 times variance of group 3, so on and so forth, and then just take that all over n1 minus n2 minus n3, n1 plus n2 plus n3 plus blah 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 minus however many sort of groups I have in there, right? So it's just a simple extension of your pooled variance estimate that we've been using before. If I've got different sample sizes and I've got different variant, and I have violations of homogeneity of variance, this might be a more effective way to go through and calculate my standardizer here. Okay? Or you use standard deviation control group. Nick, what is standard deviation control group? What is this? I'm using the standard deviation, my control group as my standardizer. Where have we done that before?
Wouldn't that be from your table?
What's that?
Wouldn't that be from your table?
Yeah, we get it from the table. What do we call this when we calculate an effect size using standard deviation of the control group as a standardizer?
Dill?
Yeah, it's just a delta estimate, so the same type of thing, right? So again, nothing much different than we're doing here, but again, when we're selecting our standardizer, we want to go through and say, all right, what's going to be the best representation of variability that we would expect? We've got more groups. We need to think of it a little bit more clearly about how we're going to go through and do this. Okay, so again, note that in order to just plug our value of our contrast in for our effect sizes, coefficients need to meet a standard set. So either 1/2, 1/2, -1, cool, right? 1, 1, -2. This is a linear set, right? Because if I had 1 and 1 and -2, I get 0. Is this a standard set? No, because 1 plus 1 plus 2 is 4, right? So basically, I've sort of my scaling up here is different than the scaling that I'm using down here, and then that screws things around. So you just want to be careful of that. Okay. Questions on this? All right, cool. Let's take a quick break and we'll jump into SPSS stuff when you guys get back. Okay. All right. Want people to open up the one-way plan contrast data set. Okay. And then have your one-way ANOVA plan contrast handout here. That's what we're going to go through and look at. And so what we've got is a hypothetical data set where, again, sort of building on the same examples that we've been working with, and we have, this time instead of ratings of valence and arousal, we have subjective ratings of amusement rated from 0 to 8 in a pilot study of not just white non-Hispanic, black non-Hispanic, and other groups, but here we're breaking things down. We got a small pilot of white non-Hispanic individuals, black non-Hispanic individuals, Hispanic, and Asian participants. Okay, and so again, the idea is we have this affective stimuli that's intended to elicit amusement, but social psychology, cultural things like that, we know that sort of there are cultural differences, and sort of people respond more strongly maybe to individuals and characters who are similar to themselves. And if we have a stimuli that just depicts white actors, that maybe, so we might have different levels of effect across different racial ethnic groups. And so we've got 4 different categories here. Small pilot, just 6 people in each group. And what we want to do is we want to go through and test whether or not there are omnibus differences. So what we're going to do is we're going to go to Analyze, go down to Compare Means, down to One-Way ANOVA, select that, and then we're just going to take emotion, rating amusement, put that in our dependent list, race in our factor list, and then for right now we're just going to go down, we're going to click Options, and say Descriptives, Homogeneity of Variance, and our Welch test. Okay. You hit Continue, and then I'm going to hit, you guys hit Paste, I'm going to hit OK. And what we've got now is our one-way ANOVA model. Okay? And as before, we can take a look at this, interpret this pretty straightforward. Here we have our means, our standard deviations, confidence intervals, min-max for each one of our groups. Here's our Levine's test. Amelia, what's our Levine's test telling us here?
So which one is Levine's?
Our test of homogeneity of variances here.
There's no significant difference.
Yeah. So we don't have, now this is we don't have, not a particularly powerful test, we only have 6 people in each cell, but it doesn't look as though we have problems with differences in the variability of amusement within each one of these groups, okay? So we've got equal cell sizes, and we don't have violation of homogeneity of variance, at least sort of based on what we can see here. So this is nice because this is starting to fall into play with our assumptions of our classic ANOVA, right? If we go down through and take a look at our ANOVA table, Haley, what are we concluding based on our omnibus test?
You would say that there's a significant difference?
Yeah, just looks like we have evidence of a reliable difference somewhere between at least one group and at least one other group somewhere in this mix, right? But we've got 4 different groups, so that difference could be coming from a lot of different places. And down here we have our Welch test. We don't have to worry about that because we didn't violate our homogeneity variance, so we're good to go here. Okay, so we have evidence of a reliable difference, and so what we've got, if we go flip to the next page, what we've done is we've set up 3 specific contrasts, right? So we're saying that based on research evidence, things along those lines, that we have some very specific predictions that we're going to make about how these means differ, or how these groups differ. Now, this isn't based on anything, this is just something to put together for a didactic, but we're saying before we run this, we have 3 individual ways that we go through, 3 specific comparisons that we want to make, all right? So, our first comparison, we're saying that white participants will be more responsive than our non-white participants, okay? So what are our weights going to be, right? What groups are we comparing? Whites.
To black, Hispanic, and Asian.
Yeah, to everybody else, right? So what are our weights going to be for this contrast? What's that?
Negative one.
Okay. How many groups do you have in the first group?
One.
One. So what's our group contrast, or what are we going to be there?
One.
One. How many groups do we have in the second group, in the second comparison? 3. So what are our contrasts going to be, our weights going to be there? Negative 1/3, right? So, and this is going to be important because we need to make sure that we have things in the right order here. But for comparison 1, my groups are going to be, my weights are going to be 1, negative 1/3, negative 1/3, and negative 1/3. Okay? 2, I'm expecting my white Hispanic and my white non-Hispanic participants are going to be more responsive than to the film than my black participants. Okay. So how many groups am I looking at in my first contrast here, or my first group? 2. So what are my weights going to be? 1/2. And how many people? How many groups in my second comparison? 1. Right. So here, what's my first weight going to be if I've got white non-Hispanics in my first one? 1/2. What's my next weight going to be?
1/2.
What's our next group? We got our black non-Hispanic group. So what's the weight for that going to be?
Negative 1.
Negative 1. What's my next weight going to be?
1/2.
1/2. And what's my last weight going to be?
0.
0. Right? Okay. So what we're doing is we're going through and we're taking a look at the comparison of my white non-Hispanics and my white Hispanics compared to those black non-Hispanics. And sort of my Asian participants are not being included in this contrast. And then my last.
So you keep them in the order that they're listed in?
Yeah, no, you need to, I mean, this is going to be important for making sure that you're attaching the right means or the right weights to the right means, because otherwise you're going to get all turned around.
Okay.
So my last comparison, I'm saying that black participants are going to be less responsive than Hispanic or Asian participants. Okay? So how many people in my first group, or how many groups in my first set? 1. How many groups in my second set?
2.
Okay, so what's my first weight going to be?
0.
Well, yeah, because white, non-Hispanic aren't involved. Second weight? Negative 1, right? Because we're saying black Hispanic are going to be less responsive, so we would say negative 1. And my last 2 weights?
1/2.
1/2 and 1/2. Okay. People see how we've gone through and created these weights here? Okay, so what I've got, based on my omnibus test, is I've got 3 specific comparisons, right? And I need linear contrast to look at this because they're not just sort of this group versus that group, right? I'm looking at combinations of different groups, not in this case, but like hopefully based on some theory and expectation based on what's going on, okay? Now the nice thing is I can look at these in SPSS pretty easily. So I'm going to go back through and I'm going to go to Analyze, Compare Means, and go down to one-way contrast, or excuse me, one-way ANOVA, okay? And we got to keep everything here, except this time I'm going to go in, I'm going to click on contrasts, okay? Now, this is going to be a pain because the way the interface is set up. But what I'm going to do, so if we look at the values, the weights that we set up for our first contrast, and this is where I'm at, that you need to have these in order because it's going to put these weights in order of how you've ordered your groups. So my first weight is going to be 1. I'm going to hit Add. And I'm going to click back on this one. My second weight is going to be 1/3. Or excuse me, negative 1/3. But I can't put 1/3 in here. So I'm going to put in negative 0.33, and that's all it's going to give me. All right. But I'm going to hit Add, and then negative 0.33, Add, negative 0.33, Add. Okay. And so this is going to be my first contrast. Then I'm going to hit Next. Next contrast, first value is going to be 0.5. So we go 0.5, add -1, add 0.5, add 0, add. Okay. Now this is tedious and time consuming, so I'm going to hit continue here. I'm just going to go ahead and I'm going to hit paste. Okay. I'm going to hit paste, and you'll see here in your syntax, your contrast statements follow a pretty easy pattern. So I'm just going to copy this, paste this down, and now instead of having to step through that stupid pull down menu, I'm just going to add in, enter in my last one. I'm going to go 0, -1, 0.5, and 0.5. Okay. This is a nice way, particularly if you're going to look at multiple contrasts. Just running through the syntax is kind of more efficient than sort of going through and punching in stuff in SPSS. But what I've got, or in the pull down menu. So, but what I've got here is I've got my one-way ANOVA that I'm going to run, and then I've got 3 specific contrasts that I'm going to take a look at. Okay, people follow me up to this point? All right. So you can go highlight that. I'm going to run it. All right. So, this is redundant, this is redundant, this is redundant, this is redundant. We've already looked at all that stuff, right? So we don't need to worry about that. But what we're going to go down through now is go through and take a look at our contrast table. So always, always, always go through and look at your contrast coefficients and make sure that you've applied the right weights to the right groups, right? So contrast 1, we're going to be comparing white non-Hispanics to everyone else. Looks good, we did that right. Second contrast, we're going to compare our white non-Hispanics and our Hispanic participants to our black non-Hispanic participants. Our Asian participants aren't involved in this contrast. Cool, we've got that one right. Here, we've got our third contrast, we've got our white non-Hispanic compared to our, our black non-Hispanic compared to our Hispanic and Asian groups. White non-Hispanics aren't included in this contrast. So we've gone through and made sure that the weights that we've assigned map onto and are actually reflecting the comparisons that we're wanting to make here. Okay? Then we drop down and we take a look at our contrasts. Okay? You'll see equal variance is assumed, equal does not assume the equal variance is. This is using the first set of equations that we presented in the slide. This is our second set of equations. Now, which one of these do we use, Nick?
This one you're going to use the first one.
The first set, right?
With the
Yeah.
thing.
Yeah, we've done here we're fully within our right to capitalize on aspects of the design, right? We have equal cell sizes. We have not violated homogeneity variance assumptions, and so we feel comfortable moving forward with sort of pulling things, sort of just going through and taking a standard approach to this. So again, if I take a look, I see that I don't have, we failed to reject the hypotheses for our first contrast that our white non-Hispanic folks are going to be more responsive than our black non-Hispanic, our Hispanic, and our Asian folks, right? So we, based on these analyses, we don't have sufficient evidence to claim a reliable effect, right? But if we go down through and we take a look at our second 2 hypotheses, assuming that we're evaluating these per comparison error rates, we would claim support for, yeah, it does look like, based on our tests here, that our white non-Hispanic and our Hispanic folks are responding with higher levels of amusement to this film than our black non-Hispanic folks. And finding that looks like in general our Hispanic and Asian participants are more responsive than our black non-Hispanic folks. Okay? So here we've got the value of our contrast. This is literally the difference in the average means across sort of our different groups, right? Here's our standard error estimates. Here's our test statistic, degrees of freedom. Notice that we've used 20 degrees of freedom here, right? Amelia, where's this 20 degrees of freedom coming from?
It's going to be the error.
Yeah, the error up here. This is coming out of our ANOVA table up here, right? Is this giving us a more powerful test? Yeah. Now, we're not running pairwise tests here, so we couldn't actually, that starts to get complicated. But what we're doing is we're capitalizing on the design here and maximizing our power and then our significance, right? Let's say we wanted to apply a Bonferroni correction to this. What would our new Bonferroni p-value be here?
No, 5 times 3.
What's that?
We know 5 times 3,
Not times 3.
or divided by 3.
Yeah, so what's that?
0.0166.
0.0, yeah, so let's say 0.017, right? And so this meets criteria, because that's, or this fails to meet, because that was not there before. This now looks pretty good, but it starts to become marginal on our Bonferroni correction, right? Because our critical value, or our sort of threshold for P, 0.017, it's 0.016, so when we corrected, that just barely made threshold, right? And so this is where we start to talk about the reduction in power as we start to add corrections. This thing that clearly did meet statistical significance based on our rules now is just barely eking over the edge if we went through and Bonferroni corrected for these three. And then this one is still looking pretty good here. Okay. People see how we went through, calculated, got these from SPSS. Okay. Let's go through and do an example if we were to calculate this by hand, just so that you can see what that looks like. Okay. So first thing we need to do, if we're going to run one of these by hand, is we want to calculate the value of our contrast. That's always going to be the first thing we want to put together, right? So value of our contrast is going to be our weight. So what's our first weight for our first set of contrasts?
1.
1 times, what's my mean for my first group?
5.
5. Okay. What's my second weight? Minus 1/3. What's the mean of my second group?
4.33.
4.33 minus 1/3. Mean of third group? 6.17 minus 1/3. What's the mean of our last group? 6. Okay. This is my linear contrast. This is just the sum of my weighted values, or my weighted means right here. Okay. So if I go through, run this out, this is going to be equal to 5 minus 1/3 times 4.33 plus 6.17 plus 6.00. Okay. So literally you can see basically what this is it's my first group minus the average of my next 3 groups. Okay. We run this out, this is going to give me a value of my contrast of negative 0.5. People see how we got the value of contrast here? Okay. So we, with our hand calculation, contrast is equal to 0.50. Okay? Saying that literally, because we have a standard set, we're saying that my white non-Hispanic folks on average are scoring about a half a point higher in response to this video than the combination of my black non-Hispanic, Hispanic, and Asian groups. Okay. Now, if we would have used different contrast values for this, it won't change my statistical test, but this value is going to change, right? And so you want to make sure that you're specifying a standard set if you're going to use stuff here. Okay. Last thing, if we take a look at my effects table, what's the value of my contrast that SPSS is coming up with? Negative 0.45, right? Why do I have a difference there?
Because we're using, our sum is 1, they're using 0.99.
What's that?
Because we're using, it's not, the coefficient isn't 0.
Okay, yeah, so this is part of it. you get a footnote here that says the sum of the contrast is not 0, right? So because we're using precise values and we had to enter 0.33 into SPSS, that's going to give us a little bit of a difference. What else is going on in terms of why are we getting a different value here? Did this mean exactly 6.17? Probably not, right? And so if you go through an SPSS and you double click on your output, right, and you double click on a cell, it'll actually pull up the value that it's got in there, right? And so we're seeing some deviation because in some ways we're more precise because we're sort of actually using 1/3 as our value of our contrast. In other ways, SPSS is more precise because we're rounding these to 2 decimal places, and SPSS has them like this many decimal places. So this is what we're getting, but we're in the ballpark, we're close. Okay. Questions about how we got the value of our contrast here? All right. So value of our contrast is.
Does the positive and negative sign matter?
It doesn't matter. I mean, you just need to make sure that you know what you're interpreting and which group is higher than which other group.
Okay.
Okay. So now what we need to do is we need to calculate our standard error for this. Okay. So standard error is going to be the square root of the mean squared error times the sum of our squared weights over cell sizes. Okay. So what is my mean squared error here? What value am I going to start with? Anything, Kate?
Sorry, I was trying to see
Oh, what's my mean squared error? Someone help us out?
Between
What is our error? Is our error between or within?
So
There, where are we seeing error? Across means or within groups? Within groups, right? 0.908, okay? People see where we're getting at? From our ANOVA table? Right up there. Remember, this is our mean squared error is just your pooled within cell variance, right? So again, so our mean square within, this is our error term, okay? So our within group, anytime you hear within group, that means error, okay? So we got our within group error, and now we're gonna multiply this times the sum of our squared weights over our sample size. So here, my weight is 1 squared over 6 plus, you're gonna be negative 1/3 squared over 6 plus negative 1/3 squared over 6 plus negative 1/3 squared over 6. Okay? That's just the sum of our squared weights over our samples. Okay? And so if I run this out, it's going to be square root of 0.908 times, what's 1 squared? 1, right? So if I take 1 divided by 6, we'll call this 0.167 plus, if I take 1/3 and square that, divided by 6, and then just add 3 of those, multiply it by 3, it's going to give me 0.333, okay? Which is going to give me a standard error of 0.674. Okay. People see how we got that? You bastards. All right. So we got standard error is 0.674. Okay? People comfortable with this? Summations can be kind of tricky. We just want to make sure that everybody saw how we got that all added up. Okay. So now, we're good to go, right? our t at this point is pretty easy. How do I calculate my test statistic? What do you think, Laura?
Let's see. You can put linear contrast over standard error.
Yep, just give me my linear contrast. The difference that I observed over the expected difference just based on just sort of deviation based just across samples, 0.674. Gives me a test statistic of 0.742. Is that going to be statistically reliable?
I guess it's
Is 0.742, is that going to be a reliable test statistic?
probably not.
No, but we know for sure no, right? If we go through and we like take a look at T-crit with how many degrees of freedom?
20.
20, right? And Amelia, where do we get that?
That's going to be the DF error.
Yeah,
No
my
critical.
degree for is error. My critical value here is going to be 2.086. Okay, this clearly does not exceed that, right? So we know that we're not going to claim statistical significance. We could go through and calculate a p-value. We could get a p-value for this using our calculator. Get a p-value for that if we wanted to, but we already know that it's not going to be statistically reliable. Okay, there we go. All right, now if we go through and we take a look at the test statistic that we got from that we calculated by hand versus what SPSS is giving us, we're noticing that our test statistic is different, our standard error is different, right? But again, this starts to speak to when we're working with small numbers and decimals, how rounding stuff starts to make a big impact, right? If you're curious and want to make sure that this is actually the formula that I've given you actually produced this type of stuff, if you go into like Excel and you double click on, you open up an Excel sheet and then double click on your output here and actually paste in sort of the actual values into an Excel sheet and then sort of use Excel to calculate this stuff up, it comes up very close, right? But your hand calculations here are going to be a little bit different. Okay. Questions on how we got our t-test here? Okay. Let's say now though that we want to got t equals 0.742, t crit with 20 degrees of freedom equals 2.086. All right. Let's say we wanted a confidence interval around this mean, around our point estimate. Think, how are we going to do that?
You're gonna take the difference between your 0.5 value
Yeah, value contrast.
plus your t times the standard error.
Those are mine. Which t?
The critical t.
Right. Okay. 2.086 times what?
Your standard error.
Standard error, right? This is nice because everything all lines up nice and even, Steven. We go through and we do this, and we go through and we calculate confidence interval here, negative 1 point. Actually, you know what? I should have made a point of. So this our value of our contrast is actually negative up here. Okay, missed that. What does that mean? Who had the higher amusement ratings? Our white non-Hispanics or everybody else? Everybody else, which is hard to know what to make of this because it didn't turn out to be statistically reliable anyway, but it actually is going in the opposite direction of what we had predicted, right? So an important thing to think about there. So if we go through and keep this true, our confidence interval ranges from negative 1.91 to 0.91. Okay. So this, we're going to interpret this as, so our best guess for based on the data that we've collected, is that white non-Hispanics are rating this film as about a half a point less amusing than the combination of black non-Hispanics, Hispanics, and Asians. But based on the data we've collected, we would expect values for the true difference in these populations range anywhere from negative 1.91 points to positive 91 points, right? So again, we're just interpreting this confidence interval the same way we would interpret any confidence interval. We're just making sure that we're sort of talking about the right point estimate. Okay. And then finally, what would be, what's the last thing we might want to do here? What do you think, Haley?
Effect size?
Effect size, yeah. So what might we want to use? So numerator's easy, negative 0.50, right? What could we use for our denominator?
That's the root of your MS error?
Yeah, fantastic. Why would that be a good choice for our standardizer?
Because you have equal group sizes.
Yeah, I've got equal group sizes and more importantly, what's going on?
Equal variance.
Equal variances, yeah. In this case, I haven't violated homogeneity of variance assumption, right? I have equal cell sizes. So I can just go up to my ANOVA table and pull the mean squared error. Mean squared error is just a pooled variance within each one of my groups, right? So I go D, the square root of 0.908 is going to give me an effect size of 0.52, okay? So I could interpret this as, so even though I didn't find a statistically reliable effect, right? Or a statistically reliable difference, my estimate of effect size suggests that my white non-Hispanic participants are rating this this film as about a half a standard deviation less amusing than the combination of my black non-Hispanic, Hispanic, and Asian folks. Okay. What do I make of this? What do you think, Nick?
It's possible that there is an effect with your small sample sizes.
Yeah, right. I mean, as a pilot study, I got 6 people per cell. That's wildly underpowered, right? So even though I didn't claim it, I didn't find evidence of statistical significance in these data, my effect size suggests that there may actually be something around a medium effect in terms of average ratings in population of white non-Hispanics versus black non-Hispanics, Hispanics, and Asians. And what else is interesting about this effect size?
It's the opposite.
Yeah, it's in the opposite direction of what I expected, right? So my idea, reasonably so, was like, okay, I'm showing participants a film stimuli containing white actors, and maybe this is going to be less effective in eliciting amusement for people who are not white non-Hispanics because of sort of social psych and sort of responding to it. So, but what I've actually found based on this pilot, well, based on this pilot, I can't say that there's any difference. But if I look at the effect size, it looks like I might actually have something going on in the opposite direction, right? So these are things that start to become important in thinking about sort of different approaches and sort of taking in total all of this put together. Okay. Questions on this? Okay. Last thing, so this is all how we would go through and do this by hand, and this is a good thing to know, okay? If I wanted to calculate a confidence interval around my contrast, do I need to do a bunch of stuff by hand? Yeah, a little bit of stuff by hand. I mean, how can I calculate my confidence interval around my effect size here, or around my value of my contrast here?
Oh, should occurred by standard error.
What's up? Yeah.
Occurred by
I
standard
mean,
error.
everything that I have, and so this is the thing. As you're going through and doing this stuff, don't do things, don't make it harder than it needs to be. Like if you've got values in your output, use your output. That's what all this is for, right? So you don't need to crank out a bunch of, if I say, here's the data, unless I tell you to do it by hand, let SPSS do it, okay? So here, what I can do, if I wanted to get a confidence, and maybe not get a confidence interval around that because it's not statistically reliable, maybe contrast 3, right? I've got the value of my contrast, I got my standard error, I can look up what my critical value is with 20 degrees of freedom, right? I just go through and calculate my confidence interval based on information provided there, right? So don't work smarter, not harder in terms of some of this stuff. If there's values that you can pull from your ANOVA stuff, go through and do that. Okay. Questions about how to go through, analyze, contrast, set this stuff up, any of that? Cool. All right. Let's jump back into last few slides here on post-hoc test stuff.
In SPSS, really quick, how do you make it so that you can see your syntax file?
Oh, you hit paste, like on any of your, what do you mean?
Well, mine's not, my syntax file isn't popping up separate.
We go to analyze. Yeah, and go to compare means, one-way ANOVA.
And when you hit paste, it pulls it up?
Yeah,
Okay. So instead of okay,
yeah.
got it.
There you go. All right. So this is our contrast. This is the high road. This is the methodological high road of going through and saying, all right, I've run this design. There's a lot of different things I could look at, but based on my theory and my research question, this is the set of things that I want to go through and look at that's most important, right? But sometimes we're running stuff that's exploratory, or there are aspects of our design. This piece is a priori, but I've got other stuff that I don't know how things are going to turn out, but I'd like to go through and take a look just to see, right? This is where we get into our post hoc comparisons. If we're looking at in a situation where we have an exploratory questions, right? We're like, I don't know how this is going to turn out because no one's actually looked at this, but I want to just go through and take a look. Oftentimes, depending on the complexity of our design, there could be a lot of different things going on in terms of sort of differences we can weigh, and we can rack up a lot of different tests. So what we want to do in these designs is make sure that we're going through and providing some type of correction for the fact that we're running a lot of different, often pairwise tests, okay? Different post hoc procedures that we can use. Fisher's, Tukey, Newman-Kuhl, Chaffee, Dunnett, a lot of different approaches that people have taken to correcting for exploratory designs. Some of these are better than others, okay? If we're talking about Fisher's LSD, basically this is a classic approach where Fisher's is just saying, as long as I have a specific omnibus test, if that F-test in my omnibus test is statistically reliable, I can go through and I'm just going to proceed looking at all possible pairwise comparisons without correction, okay? Fisher's is basically an uncorrected test, okay? Pairwise comparisons are examined using independent sample t-tests. Note that our independent sample t-test with Fisher's is going to be mean 1 minus mean 2, but then we're just taking our mean squared error, divided by the size cell, cell 1, mean squared error divided by the other cell, comparing this against critical t with degrees of freedom error pulled from the ANOVA table, right? So basically, this is just the pairwise test that we presented in the a priori stuff, right? This is just a standard old t-test, but what we're doing is we're using our mean squared error from our ANOVA table, and then we're also comparing it against a critical value using degrees of freedom from our ANOVA table as well. Fisher's, powerful, okay, but criticized for doing basically nothing to manage pairwise comparisons across multiple stuff, okay? If you've got a simple design, only 3 levels, right? So you've got 3 different groups, you can maybe get away with Fisher's, but basically this is not correcting for anything. Also capitalizing on the power of your test. The only entry for Fisher's is saying you just have to have that omnibus test. Once you got the omnibus test, go nuts, okay? So this starts to become problematic in all cases except for those with a very small number of factors. Okay. People see how we're getting fishers? Okay. Big one is Tukey's. Everybody loves Tukey, right? But Tukey's a little bit complex in terms of how you go about in calculating this. But if you know how the ins and outs of how Tukey is calculated, you can use this a little bit more flexibly with things. So Tukey and a number of other post hoc procedures based on what we're calling a studentized range statistic. I gave you a handout. You've got a Q table. Look at this, our Q statistic. In calculating your Q statistic, Q is calculated as, your test statistic is calculated as the difference between the largest mean and the smallest mean in your set over your mean squared error divided by the cell size. Again, this is assuming a balanced design in classic Tukey. Okay? And so what you would do for Tukey tests is you would go through and you take a look, calculate your test statistic, and then what you would do is you would compare that against a critical value pulled from your table. Okay? So let's say I have 4 means, right? I've got a one-way design with 4 levels, right? What I would do to determine my critical value for that, and let's say I have 20 degrees of freedom in my mean squared error, right? What I would do is I would look into R is given as the number of total means, so I would go through and look at 4 in my upper column, go down to 20 degrees of freedom, and I would say the critical value that my Q statistic needs to reach is 3.96. Okay? People see this? Okay. Now, note that Q has a direct relation with T. Okay? Our T statistic, calculated, again based on this, is calculated as the difference between means over the square root of 2 times the mean squared error over n. Okay? I mean, essentially we're just taking this, instead of taking this plus this, we're just saying 2 multiplied by this, right? So functionally what ends up happening is we can go back and forth from Q and T by a simple conversion. T is our T value. If I take my Q statistic and divide it by square root of 2, it's going to give me my T. If I take a Q and if I take a T times the square root of 2, that's going to give me a Q. I can move back and forth between these, and this starts to become important later on when we start wanting to use Tukey maybe in a more flexible manner. Okay. So, primary difference between our T criticals and our Q criticals is that our Q critical is going to be based on the number of means in our set, right? So as for Layla, if you're looking at your Q table here, for 20 degrees of freedom, what happens to our Q critical value as the number of means that we're looking at start to increase?
As the degrees of freedom.
No. For 20 degrees of freedom, what happens is the number of means I'm comparing. As the number of means I want to look at increase, what does my critical value for Q do?
Increases?
Yeah, it's getting bigger, right? Because I'm making more comparisons, right? If I've got 3 comparisons, if I've got 3 means, how many pairwise comparisons can I make? With 3 means? 3, right? If I take K, what is it, times K minus 1 over 2, that's going to give me the number of unique pairwise comparisons I can make. So if I've got 3, I've got 3 times 2 is 6, divided by 2 is 3, right? If I've got 4 means, how many comparisons can I make, pairwise comparisons? Unique pairwise comparisons can I make with 4 means? 6, right? With 5? 10, right? So what this is doing is Tukey is correcting for, it's assuming that you're going to make all possible pairwise comparisons. So as we start to increase, the number of tests that you're correcting for increases. So you see that Q, the critical value for Q starts to increase with the number of steps because we're accounting for larger and larger and larger number of tests, right? If I have 10 means, if I got a factor with 10 levels to it, right? Or I'm making 10 pairwise comparisons, how many, if I've got 10 groups, how many possible comparisons do I have? 45, right? That's a lot, right? So we have to have a bigger penalty for those tests. And so this is one way we can go about doing this, all right? So again, here's our larger test. How we go about using this, there's a couple different ways, and depending on the variant of Tukey, this is gonna change a little bit, okay? The assumption is that if I don't have any a priori hypotheses, I go through and I run my ANOVA, and I get a significant omnibus effect. What happens is I go through and then I look at my descriptives table, and I'm like, hey, I wonder if that's different, right? And so I start cherry picking different means. Like, that one's a lot different than that one. I wonder if that meets statistical significance. I wonder if that one and that one is different. I wonder if that meets statistical significance. Visually, what have I done by looking at that table of means? Functionally, I've just ran all possible pairwise comparisons in my head. Not technically, but I've gone through and I've looked at them, and I've sort of looked to see which ones are higher. And so basically, Tukey's assuming I've already gone through and I've made all possible pairwise comparisons, right? I just did that by looking at it. And so what happens if I start cherry picking those means that are sort of the farthest apart, I've dramatically increased my possibility of creating a type 1 error, because I've gone through and I've specifically chosen the ones that are the greatest distance and probably have the greatest likelihood of committing a type 1 error. So Tukey's assuming if you're using this, as soon as you look at the means, you've already done all possible comparisons, so now we're going to correct for those. And so for the classic Tukey procedure, what we do is we order our cell means from largest to smallest, or smallest to largest. So 4, 10, 11, 24, 29. In this case, we have five groups, 8 people in each group. Degrees of freedom error 35. Our mean squared error is 32. This is pulled from our ANOVA. Okay. So what we would do is we take our cell means, order those means from largest to smallest, and then I want to determine the number of steps between means to be compared. So if I want to compare x1 and x2, that's 2 steps, right? If I wanted to compare x1 and x5, that's going to be 5 steps. And then Tukey says what we do is we then calculate a test statistic or Q statistic for that specific comparison. So let's say I'm looking at the comparison of mean 1 and mean 5, right? The biggest one that I've got. What I'm going to do is I'm going to take in the numerator, I'm going to take sort of this mean minus that mean, so the comparison of my 2 means, and then I'm going to take this divided by my mean squared error over my cell size is 8, and it's going to give me a test statistic of 12.5. Okay. Then what I do is I go to my Tukey table, and I go through and I say, okay, what's my critical value for 35 degrees of freedom with R equal 5, because that's the number that's the distance between those two. I go through and I pull that up, I take a look. That's not going to be a value that's presented on the table because it's in between 30 and 40, but I have a critical Q of 4.07. Okay. My test statistic exceeds my critical value, and so I would claim statistical significance at alpha, or at p less than 0.05. Tukey doesn't give you a specific alpha level. If you look at on your handout, this first table is for alpha 0.05. Second version is alpha 0.01. Classically, you don't want to get a specific p-value for Tukey. SPSS will calculate one for you, but from the classic approach, you would just report this as p less than 0.05 based on your Tukey, or p less than 0.01, so on and so forth. Okay. Now, if I were to be comparing, let's say this is 40 degrees of freedom instead of 35. Let's say I'm comparing mean 1 against mean 2. What would be my critical value there? Yeah, 2.86, right? So from a classic Tukey approach, what we would do is we would go through, and as sort of the difference between my means increases, that starts to increase my my critical value that I'd use from a classic approach. Yeah.
So you always use the degrees of freedom for the full set, not just
not for this
for the cell.
For the classic approach, we're going through and correcting for each one of those, right? So if I want to compare this group and that group, what's the R for my critical value? 4, right? If I wanted to compare this one and that one, what's the R that I would use? 3, right? So from the classic approach, each individual test is going to have a different critical value.
I meant like for the degrees of freedom. You do it for the full set regardless of which one you do, not cell by cell.
Yeah. Degrees of freedom is always going to be pulled from your overall ANOVA table. Okay. All right. So incidentally, so looking at this is specific to, it's similar to t-test, but we're not just giving a specific p-value, it's just p less than sort of whatever. Okay. People kind of see how this approach works. Now, a couple of different things we can do with Tukey to make this a little bit more flexible. What I can do is I can go through and I can determine the critical value necessary to claim statistical significance for a t, right? Let's say I've got an ANOVA, 6 levels in a factor, so I've got 6 means, right? I've got degrees of freedom error is equal to 47, right? If I want to max out, if I want to compare things at the max, at the most stringent Tukey value, my critical value, Q critical for 6 means, 47 degrees of freedom is going to be 4.23. Okay, so if I go through and you can't find it in this, you have to use an online calculator, but at alpha 0.05, R equals 6, degrees of freedom 47, my critical Q is going to be 4.23. But because I know that Q has a direct relation with T, what I could do is then I could work backwards and I could say, all right, well, this is my Q critical, what's my T critical? Well, all I need to do is I take 4.23, divide that by the square root of 2, that gives me a T critical of 2.99, okay? So note that a T critical for just 47 degrees of freedom at alpha 0.05 is 2.02. So the conversion from my Q critical to my T critical is a much more stringent value, right? So sort of displaying that what we've got here is a correction for multiple comparisons. And then what I could do is then I could just run through and run in SPS I can just run test statistics, right? And any t-test that I run where my test statistic is 2.99 is going to be interpreted as significant at p less than 0.05 with my Tukey correction. Okay. Now, asterisk here, because this isn't exactly a direct application, because if I'm running my t-test, what am I using for my variance estimate with my t-tests, individual or between subjects t-tests? I'm just using the variance from each one of my individual cells, right? Now, classic Tukey is taking the mean squared error from your ANOVA table, right? And so it's a little bit different. But we'll talk about this as a potentially effective way to go about trying to provide some correction for more complex designs. So other thing we can do, so we can go through and derive a rough critical T, a corrected critical T for that's associated with Tukey. Or what I can do, I can just go through and physically calculate the difference in means that I need to find as statistically significant. Again, let's say Q critical is 4.23, alpha 0.05. I've got 6 means, 42 degrees of freedom. My mean squared error, let's say, is 32 for my ANOVA table, right? So if my Q is mean 1 minus mean 2 over the mean squared error of divided by my sample size or my cell size, then the difference in means that I need to achieve statistical significance with a little bit of algebra is going to be Q times the mean squared error over my cell size. So what I can do here is I can go through and plug this in. So what's the difference that I need between means in order to achieve statistical significance? Well, if I take my Q, multiply this by the mean squared error over my cell size, gives me a value of 8.46. Then I can just go through and look at the difference in means. If the difference in means exceeds 8.46, then it's statistically significant at p less than 0.05 based on my Tukey conversion. Okay, so a lot of different ways with a little bit of algebra I can go through and set this up. Functionally, it should be all about pretty much the same. but different ways we can go about and sort of using this to be a little bit more flexible. Okay. Questions about this? All right, so this is sort of the nuts and bolts of Tukey, but depending on what type of Tukey approach, going to be slight tweaks with this. Tukey's HSD. This is probably the most common. This is the one that everybody. This is the classic Tukey that people like to apply. With Tukey HSD, we're going to compare all pairwise contrasts at the maximum values of QR, right? So before, when we talked about sort of the initial setup, depending on how far apart my means are in sort of the order, that's going to determine the R in my critical value. Tukey HSD says, well, we're just going to use the max critical value for all comparisons. Okay, this is the correction. If you just request Tukey in SPSS, it's Tukey HSD. You're not getting different critical values for different tests. It's saying what's the total number of means that you've got? All right, we're going to set the R value and the critical value equal to or identical for all of those. So for a factor with 5 levels, all means are treated as if they were 5 steps apart. So we're not making adjustments based on steps here. So what ends up happening is we fix our family-wise error at alpha, and what we're doing here is literally we're comparing, controlling for all possible pairwise comparisons within this set. And again, we can determine how many tests that we're correcting for based on the number of means minus, or the number of groups multiplied by the number of groups minus 1/2. That's going to tell us how many pairwise tests that we're having or correcting for. Okay. Then we would go through and test those contrasts against a Q critical if you're calculating Q statistic, T critical if you're running independent sample tests, recognizing that this test statistic is calculated a little bit differently than how it's intended in Tukey, or the minimum difference required for all of these things. Okay? So again, Tukey, one of the most popular post hoc testing procedures, good protection against type 1, but if we have all possible, let's say I've got five groups, right? And so how many pairwise comparisons is that? Am I correcting for? 10, right? What if 10 comparisons? Not all 10 comparisons are interesting. What if only 4 comparisons are interesting? Well, I'm still getting penalized for 10, right? I can't. So if I'm going through and I'm just running a Tukey, I'm going to go through and I'm going to look at my 4 that are interesting. But I've been corrected for 10, even if 10 aren't interesting or don't maybe even make any sense, right? So you have to think about sort of what I'm doing in the approach, and this is going to be a drawback. So you're correcting for all possible comparisons, whether you like it or not. Okay? So important to remember with your post hoc test, if you just go through and you ask it to give me a Tukey, it's going to correct for all possible pairwise comparisons. And when we get into factorial designs, not all pairwise comparisons are going to be literally interpretable. There's no way to interpret them, but you're still getting taxed for them. Okay. Variations on Tukey-Kramer. If we have unequal sample sizes, right? Tukey-Kramer is nice in SPSS. This is the Tukey that you get. It's a sort of combination Tukey, HSD, making a correction for sort of variation in your cell sizes. In SPSS, we can also request a Games-Howell correction. Games-Howell is correcting for unequal samples and unequal variances. Okay, we're changing sort of a critical value. So our critical Q changes a little bit. It is a W statistic. We take a recalculation of our degrees of freedom, make an adjustment there. And this is basically simple or similar approach to our Behrens-Fisher, our Welch-Satterthwaite correction for unequal variances and things along those lines. Howell is strongly recommending this if we have unequal variances, given that if we violate homogeneity of variance, starting to pull that effect size, or that use that mean squared error as our sort of our measure of variability across groups. If we have unequal samples, we have unequal variances, I don't like that as a good measure of a specific variance estimate for the test that I'm looking at here. So Howell strongly recommends looking, recommends looking at this if we've got violations of homogeneity variance in unequal samples. Other post hoc tests, Newman-Cools, right? So this is gonna be back to, Newman Cools is gonna set a different critical value for how far apart each one of your means are, right? So this is gonna go back through, and so your Q critical is gonna be different for each one of your comparisons based on how far apart they are and things. So here, it's gonna start changing around. Newman Cools is more powerful than the Tukey honestly significant, but it's gonna give you less control, right? Tukey HSD is controlling for all possible comparisons. This is gonna be less of an adjustment here, okay? Or less of an adjustment. All possible combinations, not all possible comparisons, all possible combinations, extremely conservative. Don't use this. This is not, sometimes people are like, I use a fancy post hoc test, but generally what it means is crazy conservative and you're probably losing power unnecessarily. Dunnett's test is interesting. Dunnett's is comparing a reference group, or sort of all of your means or all your groups to some control group. So we've got one control group and 4 experimental groups. Dunnett is just going to go through and it's going to compare each one of your experimental groups to the to your control group, and then just correct for those, right? So this can, in certain situations, this can start to become meaningful. We've got critical values based on the separate table. This is nice, it's not terribly flexible, right? We have to say, I want all groups to be compared against this group. If you have a study where that fits, Dunnett's is awesome, but that's gonna be a limited subset of things that are available, okay?
Is that in SPSS?
Yep, these are all in SPSS, okay? Which of these is best? There's not one that's gonna be best, okay? This is gonna be a determination based on what you're trying to do, how many means you've got, how you're putting all this stuff together. In general, if we have a priori tests, we plan this in advance, and hopefully you do, because you put together a study, hopefully you know enough about the background literature to say, within this, these are the things that are gonna be important. There are other things I could look at, but these are the things I'm gonna look at, right? Here, we can use contrasts, independent sample T's if they're pairwise comparisons. We can sort of correct with Bonferroni Dunn-Sidek if we've just got a small collection. Remember that these two corrections, Bonferroni Dunn-Sidek, are not for lots and lots of tests. That's going to be way too much of a correction. So you want to use this very judiciously. If we've planned tests in advance and we're looking at complex combinations of things, this is where linear contrasts come in, right? And this is cool, right? You can say, basically, I expect these two groups to be larger than these two groups, and this is why this is an important thing to test. This is where linear contrasts come in. We can start looking at things. Again, we can correct with Bonferroni Dunn-Sidek if we have sort of want to have just be extra careful with that. And then if we have a large set of exploratory analyses, Tukey and Tukey variance generally recognized as sort of the most common approach, but you could maybe make arguments for others. Like anything else, if you're going to do something weird, have a good justification for it. Because if I read your paper, I'm like, this is weird. Why did you do that? Like, just either this gave you the result when the normal thing didn't, or 2, you're just trying to be creative and now it's all kind of confusing. So if you're going to do something that's not consistent with sort of convention, should make sure you go through and provide an example of that, or provide a justification of that. Okay. How are we doing? Good? Okay. That gets us through ANOVA stuff. We've got, we didn't get an opportunity to go through post hoc tests in SPSS, but that's actually a pretty straightforward thing. You just go through in post hoc in that menu and just tell it what post hoc tests you want it to run, and then it'll just run for you, and then you just interpret it. I'll go through and I'll post a screencast video walking through post hoc tests so you can go through and take a look at that. But again, your handout on the post hoc test, it's short because listing out all the post hoc, the output from the post hocs would have ended up being like 50 pages, and that's not necessary. You can just run those on your own. But again, if you go through and take a look, you can just start going through and selecting sort of different post hoc tests, and what you can do is start looking at differences in patterns of effects that you're finding with different post hoc tests, right? Because the main difference between these is the amount of correction that they put on stuff. The more severe tests, are you gonna find that some things that are significant with like Fisher's LSD aren't significant if you put a heavier correction on what like Tukey, or if you went through and got nuts and went Chaffee on something, now all of your effects disappear because that's a super conservative test. So if you're going through technology, just think about sort of how conservative these tests are and so what they're going through and doing. Questions? All right, cool. I think we're on a good track. We'll finish up the last 2 lectures with factorial ANOVA, and then we're gonna call it good. Other thing, I was thinking about, we got a couple people not here. And this semester gets tricky. You guys have a lot of stuff.